Okay, we're going to start talking about coupling with the magnetic field. We're going to look at, first we'll introduce the concept, then we'll look at two simplified models, one for a microphone and the galvanometer, uh, and then we will look after a motor, which will be what we focus on in the course. On an exams, I want you to be able to handle a motor. So we'll get to that. Uh, so let's just introduce this here. Uh, so our variables, we'll just bring them all in. V is the velocity of the conductor with respect to a magnetic field. Okay, so picture you have the windings of a motor and it rotates. So the velocity relative to the magnetic field, we'll point a little bit of stuff out here in a moment. We'll just phi, this is flux in Webers. That's the flux of the magnetic field. B then is the flux density of the magnetic field. So that's Webers per meter squared. So you kind of have this before you look at that. The force on the conductor. So if you picture, so what's the force causing the thing to want to rotate? If you have a rotor, you put a force in the conductor and that'll create a torque. Current in the conductor. Length of the conductor that is in the magnetic field. Okay. So, and then the last thing, the back voltage, which is induced by the conductor. All right. So, from physics, here are some things that hopefully you've seen. The force in a conductor is given by the current times the length of the conductor through the magnetic field cross the magnetic field. These things are generally set up perpendicular such that this is a normal situation set up to be current times conductor length times the magnetic field. And note, when this L, as your windings are set up, you could have many windings combining to create tremendously large lengths of conductor within the magnetic field. All right. The other equation is the back voltage is equal to the velocity of the conductor through the field cross the magnetic field. And that basically that'll set up the positive plus minus sense. Is it minus plus or is it minus plus for the voltage? So, which we're not going to be concerned, it's not going to be a major concern for us actually, but we'll leave. We have velocity cross the magnetic flux density, then times the length of conductor. So if you have lots and lots of conductor going through, you can build that number up. All right, power. Power in, if you have a motor, is EB times I, and the power out would be force times the velocity of the conductor going through the field. So that would be ILB times, here's V velocity. All right, there are two basic ideal models when we deal with motors. And so what you have is a current comes, you get this back voltage. All right, so the voltage drop across this. And then with whether you have a linear or a rotation or a rotary motor, you have mass or you have inertia, and that produces force or torque. So this would be a linear motor, this would be a rotating motor. You could then, either using force or torque, basically run the motor backwards. So you have mass and inertia, and that creates a voltage, and then you have a generator. So running this backwards, you get a generator, supplying current to get the back voltage, you drive the motor. So we will now, I'm going to end this right at this point, and I'll come back and we're going to take a look at a model of a microphone.